everyone. We are going to start our next unit today, and I'm just going to give you sort of a brief introduction. It's really a mini unit. Related rates is just one section of Chapter 2, but it's a really fun and interesting one, and one that shows up a lot for us on the final. So today we're going to do 4 problems, and you're really just going to see a touch of a little bit of everything, almost everything that you could see in this unit. Now, we've been differentiating or taking derivatives for a long time, and we've always talked about how derivatives are a rate of change. Well, think about a rate of change. We most often talk about rates in terms of time. So imagine, instead of differentiating with respect to x like we normally do, imagine if we differentiated with respect to time. So how would that look different? Well, to be honest with you, you already know how to do this. If we were to take the derivative of this equation right here, x squared plus y squared equals 4 with respect to time, you would very quickly say, well, that's 2x. But since we're not taking the derivative with respect to x, we would have to write dx dt, much the way we used to write dy dx every time we took the derivative of y. And when we take the derivative of y squared, it would be the same thing, 2y, but dy dt. And when we take the derivative of 4, well, that's still a constant, and that's still 0. And that's really the only difference in differentiating with respect to time. Turns out in the real world, differentiating with respect to time is a useful thing to do. So I'm going to start with this first example, which really just shows you the mechanics of it, and then we'll get into some real world problems, and this whole unit is really focused more on some really interesting problems. So the part B of this is, imagine if you were given that dx dt equals -2, and I'm going to point something out, that if something has a negative rate of change, that means it's decreasing, and we're asked to find dy dt when x is equal to 1 and y is equal to 3. Well, we're going to go back to the equation that we just wrote above, and I'm just going to rewrite it. 2x dx dt plus 2y dy dt equals 0, and I'm simply going to plug in what I know and solve for what I don't know, and in this case I'm going to solve for dy dt, and I know that dx dt is -2 and x is 1, and y is the square root of 3, so I have -4 plus 2 square root of 3 dy dt, and hopefully without too much effort we can say 2 square root of 3 dy dt equals 4, or dy dt equals 4 over 2 square root of 3, and if you feel like simplifying that, you can, and if you don't, that's okay too. You could call that 2 over square root of 3. You could call that 2 square root of 3 over 3. Any one of those 3 are correct answers. That's the mechanics of differentiating with respect to time. But let's talk about how we actually use these problems, like you'll see in number 2. Now, before we get too far into these questions, I'm going to give you a little suggestion to get started. Whenever you have a related rates question, which means you're talking about how different quantities are changing over time, I think it's wise to start with a sketch, and usually it's wise to start with 2 sketches, and then think about what's the relationship between all these quantities, and that's basically the equation. And after that, it's what we did above. We're going to differentiate and solve for what we're asked to find. So let's take a look at number 2, where we have Sheila is walking to a lake and throws a rock into the water, and we have a circular lake, and we know that the area of a circle is pi r squared. And if you read it carefully, it says that after she throws the rock in, it forms concentric circles, which means circles that have the same center, kind of like skipping stones, where these circles are getting bigger. And may not be a bad idea to draw those as 2 separate circles too. So what do we know here, and what are we trying to look for? Well, notice that when you throw that rock in there, everything is changing, right? This circle, the area of this circle is likely getting bigger. The radius is getting bigger. Remember, the radius is a segment from the center to the edge. So both the area and the radius are changing, and we are asked to find the rate of change of the entire disturbed area, meaning how fast is the area changing. Another way to say that is we are looking for dA dt. Now that means we must know what dr dt is, because that's the other variable in this equation. And if you read carefully, and I'll suggest that you look for these sort of double unit expressions where it says the rate of change of the entire radius is 1 feet per second. And now keeping track of the units can just help you keep track of what everything is. And we want to find out when the radius is 4 feet. Now remember that the radius is 4 feet for only one instant, not always. It's continuing to get bigger. So what am I going to do here? Well, I've made my sketch. I figured out, actually I was told that the relationship was the area. I'm going to differentiate, and the derivative of a with respect to time will be dA dt. Now pi is a constant. You wouldn't treat that any differently than you would any other number. So I'm just going to keep that there, and I'm going to call this 2 pi r dr dt. And now remember, I'm looking for dA dt. So let's leave that alone, and let's plug in everything else that we know. So we obviously know 2, and we know pi, and we were told that the radius is 4 at one particular moment, and we were told that the radius, the dr dt, is changing at a rate of 1 feet per second. And although I don't have to list my units, it's not a bad idea to just sort of mentally double check that they're all working out for you here. And we end up with 8 pi. Now technically, it would be feet squared per second, because remember this is 4 feet, and this is 4 feet per second, but you aren't required for me to put these units in, but area is a two-dimensional measurement, so it makes sense that that's 8 pi feet squared per second. And that's the answer. There's not a whole lot of work there, but there is a bit to think about. So let's try another problem, one that actually involves a little bit of volume. Now taking a look at the second one, we have been given the equation, we've been given the relationship, the volume of a cone is 1/3 pi r squared height, and we want to find dr dt when the r is 2 and the h is 3. And we're given even more information than that. We're given dV dt, which means the volume is changing, and we're given dH dt, which means the height is changing. So really imagine like water being filled into this cone, and we know that the radius is that segment, and we know that the height is that segment, and water is being filled into this. So the height of the water, the radius of this part of the water is changing constantly. We want to know what is that rate of change at the moment when the radius is 2 and the height is 3. So let's start by writing out our equation. And you may notice that you have a couple different variables here, which makes this a little bit more of a pain. When we differentiate, the derivative of v is dV dt, and I'm going to treat this as a product rule using the 1/3 pi to go with the r. So when I differentiate, I'll have 1/3 pi r squared. I'm going to keep that. Derivative of h is dH dt, and then I'm going to keep my h, and the derivative of 1/3 pi r squared would be 2/3 pi r, don't forget the dr dt, and it sure is messy, but that's really all the calculus, and from there we're really just going to plug in what we know and solve for what we don't know. We were told that dV dt is a half, and 1/3 and pi are constant, and r at this particular moment, remember, is 2. And dH dt we were also given was 3/4. So a little bit of a mess. And again, remember, we were told that h was 3. And again, 2/3 pi is constant. R at this moment is still 2. And we are looking for dr dt. So cleaning this pretty good sized mess up, we have a half equals, this whole mess actually cleans up to be just plain old pi, plus this whole mess turns out to be 4 pi dr dt. And in solving for dr dt, I'm going to move the pi over, and then eventually I'm going to divide by 4 pi, and I have a pretty ugly looking answer of 1/2 minus pi over 4 pi, and we could come up with a decimal equivalent, but that's basically the mechanics of it. And this one's a little bit messier than the last one because it involves a product rule, but as we go on in this unit, we'll come up with ways that we can even avoid that messiness and sub one variable in for another. Okay, let's take a look at the last one. Now, reading over number 4, this is probably the most common kind of question, and we'll spend a couple of days on questions like the ones you're seeing here in number 4. We have a picture already drawn for us. Car A is going east at 50 miles per hour. So I'm actually going to start by just making note of that. It's telling me that dA dt is 50 miles per hour. Notice that it's a rate. and it's telling me that dB dt, car B, is going 60 miles per hour, and starting from the same point, meaning starting right from there. After 30 miles into the journey for car A, well, that means car A is 30 miles away from the start point, and 40 miles for car B, meaning that's where car B is. We want to find the rate of change between the distance of these two cars, meaning of this side. Well, I hope your geometry is kicking in and you're seeing what the relationship is here, because we have no formula given to us, but you see that you have a right triangle, and we know that a squared plus b squared equals c squared. And I want you to notice that all three of these are changing, all three of these sides. So car A is starting here and it's moving along, and that length keeps getting bigger. Car B is starting here and it's moving along, and that length keeps getting bigger. And we want to know how fast is it changing, the distance between them, at the moment that A is 30 miles away from the start point and B is 40 miles away from the start point. Well, that really means we're looking for dc dt, meaning we're looking for the rate of change of the hypotenuse. I'm going to call that c. So how do we do something like this? Well, the first thing you might want to think about is what is the distance between these two? And you may recognize this triangle as a pretty well-known triangle, but I'm going to use the Pythagorean theorem and solve for c squared. And I have 900 plus 1600 equals c squared, or 2500 equals c squared, or c equals 50. Now remember that I'm putting these numbers in, but they're only true for one instant, so I don't want to substitute into here until after I take the derivative. So when I differentiate, I have 2a dA dt plus 2b dB dt equals 2c dc dt. And you may notice, and you don't have to do this, but I notice that each term has a 2 inside of it. So I'm just going to be lazy and divide through by a 2 for every single term. And again, you don't have to do that. I do that so that I have fewer terms to keep track of. And once I get here, all I have to do is plug in for what I know and solve for what I don't know. I know A is 30, and dA dt is 50, B is 40, and dB dt is 60, and at this moment in time, C is 50. And solving, I have 1500 plus 2400 equals 50 dC dt. And dividing through by 50, I end up with 78, would be miles per hour, for dC dt. So that's a whole lot, a couple of different kinds of problems, an area, a volume, and a Pythagorean theorem. You're going to see many, many more of all of these different kinds. Your homework is probably a touch simpler than what we just saw in this video. If you have any questions, email me.